Okay, in this little mini lecture video, we're going to talk about how we can quantitate the binding of oxygen to myoglobin. So we're going to start with myoglobin because its oxygen binding, its oxygen saturation follows a different process than that of hemoglobin. We've seen that we're already starting to see that through our in-class activities. So when we're talking about myoglobin binding in oxygen, we can represent that via a chemical equation. So myoglobin plus one oxygen, because we know that myoglobin functions as a monomer and it only binds one oxygen to its heme to form a myoglobin oxygen complex. So we can write a Ka for this. So before, when we were studying buffers, Ka was the acid dissociation constant. Now it's the association constant, which talks about the binding affinity of myoglobin for oxygen. And we know that with any equilibrium constant like that, it's products over reactants. So it's the concentration of the myoglobin oxygen complex divided by the individual concentrations of myoglobin and oxygen. And what we can see from this is that the higher the value for the Ka, the higher the affinity for the oxygen ligand, right? So higher the Ka, that means the larger the numerator. The larger the numerator, the more complex is present. The more complex is present means that the protein, the myoglobin, has a higher affinity for its ligand, which is oxygen. So that's great. So that's talking about binding affinities. But of course, in biochemistry, we always talk about it in the reverse. So we always talk about dissociation constants. So we talk about the reverse reaction. Oops, get a little carried away there. So this is just the reverse of the previous reaction. So I can write a dissociation constant as opposed to an association constant, which is again the concentrations of products over reactants. And now what we can see is if you have a larger Kd, that means you have less ligand affinity. So the higher the dissociation constant, that means the more broken apart the complex is, the greater the individual reactants. So you have a lower affinity of that protein for ligand, or in this case, myoglobin, for oxygen. So in the dissociation constant, the amount of the free versus the bound ligand, so here's the free versus here's the bound. So the amount of free versus bound ligand depends on the overall concentration of ligand, in this case the overall concentration of oxygen. And we saw that in our binding curves that we've been studying. And when we're in cells, or in vitro assays for that matter, but in cells, the ligand is typically in excess, much more ligand present than there is ligand binding sites. So we're talking about there being a greater concentration of oxygen than there is of myoglobin. So we want to talk about how much O2 is bound. So we want to talk about the fraction of saturation, so the fractional saturation of myoglobin, which is represented by theta, and sometimes that's represented by YO2. It means the same thing. So we've seen in our in-class activities so far that can have a range of 0 to 1, where 0 is completely unbound, no binding sites occupied, and 1 is complete saturation, where all of the binding sites are occupied. So we can write our expression for theta. It's the binding sites occupied divided by the total binding sites. And notice we're talking about binding sites. We're not talking about molecules. So I'm not saying the number of myoglobins present. I'm saying binding sites. So if we write that, the binding sites occupied would be the same as the concentration of the complex, so the myoglobins with oxygen stuck to them. And then we know that the total number of binding sites would be the concentration of the complex, so sites that are occupied, plus the concentration of myoglobin that doesn't have any oxygen bound to it. And again, this is because we remember that there is one binding site per myoglobin molecule. So then what we want to do are some mathematical manipulations in order to incorporate the KD value, this dissociation constant, which allows us to talk about how or the affinity of myoglobin for oxygen. We want to incorporate that into our fractional saturation expression so that we can relate the two. So we know that the KD is equal, again, to the concentrations of products over reactants for the dissociation reaction. I'm going to solve this for the concentration of complex. So the concentration of complex then is equal to the concentration of myoglobin times the concentration of oxygen divided by the KD value. And now I'm going to substitute this expression for myoglobin and oxygen complex back into my expression for theta. So that means theta equals the concentration of myoglobin times the concentration of O2 divided by the KD, so I just substituted in for the concentration of complex, divided by the same thing again, because I'm going to substitute in for the concentration of complex, plus the concentration of myoglobin, which was the sites without ligand bound. So remember, the top here, this part, that's going to be the total binding sites occupied, so that was equal to the concentration of complex. And this bottom part here was the total binding sites present, which was the binding sites occupied plus the binding sites unoccupied. So now we want to do some math so that we can simplify this expression a little bit. I'm going to pull out the concentration of myoglobin. Oops, I'm going to write in black. So the concentration, or sorry, not the concentration, the fractional saturation then of oxygen to myoglobin. If I'm separating out the myoglobin concentration, so I'm just going to use parentheses to do that, divided by, pulling out myoglobin again using parentheses, only this time I have this entire denominator, so I've got concentration of O2 over the KD plus 1. So that's me pulling the concentration of myoglobin out for the denominator. Now I'm going to take this entire expression and I'm going to multiply by the KD over the KD, because that's the same thing as multiplying by 1. And when I do that, I'm going to simplify things up a little bit. I'm going to end up canceling out these KDs, and one's going to end up right there. So now what I've got is the concentration of myoglobin times the concentration of oxygen divided by the concentration of myoglobin times the concentration of oxygen plus the KD value. Now that I've done that, multiplying through, I can simplify. My concentrations of myoglobin are going to cancel out. So that gives us this really nice equation for fractional saturation, where theta, the fractional saturation of O2, is equal to the concentration of O2 divided by the concentration of O2 plus the KD value. So now I've got this nice relationship between how many binding sites are occupied, this fractional saturation, and the equilibrium constant that talks about how tightly associated the protein and its ligand are. So we'll also see this written with the partial pressure of O2, because the concentration, since oxygen is a dissolved gas, so we'll also see this as theta equals the pressure of O2 divided by the pressure of partial pressure of O2 plus the KD. So that's totally fine. So if we were going to write or make a graph of this, it would look something like this. So we've got the fractional saturation of O2 here. Here's our 50% mark. I'm going to write these as percentages. Here's my 100% mark. Then here's my pressure of O2 along the x-axis. So something like this. So this is hyperbolic in shape. And we have this value right here that we're going to call the P50. So this is the pressure right here of oxygen that it takes such that you have 50% of your binding sites occupied. So we could write that out. The P50, I'm going to make a little squiggly here so I can separate this out. So the P50 equals the pressure, partial pressure of O2, when theta is equal to 50% or 0.50, right? Because this is fractional saturation, goes from 0 to 1. So I could plug that into this equation over here that we just derived. So we could say 0.5 is what we want theta equal to. That's going to be the pressure of oxygen, which we said is the P50, whatever pressure that is, divided by the KD plus the P50. Again, that's the pressure of oxygen that you have when you have this fractional saturation of 0.5. Then if we do some math here, let's multiply both sides by this denominator on the right side of the equation. So 0.5 times KD plus the P50 is equal to the P50. Then we can multiply out our 1/2, so KD over 2 plus the P50 over 2 is equal to the P50. So hopefully what you're seeing then, if we multiply through by 2, KD plus P50 is equal to 2 times the P50. And that tells us that the KD is equal to the P50. So that KD value that talks about how tightly bound our protein and oxygen are, that value is equal numerically to the pressure of oxygen that you have when 50% of the binding sites are occupied. So that means, let's write that out, when the pressure of O2 is equal in value to the KD, then you are at theta equal to 0.5. So half the binding sites are occupied by oxygen. Now it turns out that the P50 of myoglobin is equal to 2.8 torr. The pressure of O2 in blood is about 100 torr. So that's telling us that the KD value is much, much less than the pressure of O2 that's present. Therefore, that's telling us that all of our myoglobin molecules are bound to oxygen. So we are way over the KD value. So again, if we make my little sketch, because I only have 10 pages on my whiteboard, let's see, I'll just make a little sketch right here. So if this was our picture we had, and this was the pressure of O2, and this was theta, remember, here's 0.5, so this value right here is the KD. So the pressure of O2 in the blood is all the way up here, okay? So this is the 2.8 torr, is way, way low. We're way, way, way up here at 100 torr in the blood. So that tells us that we're up here on the saturation curve, which is up near 100%. So it turns out, then, this is the last thing to say about this, is that you can apply this calculation for figuring out the saturation of a protein with its ligand to any type of protein that binds a ligand. So we could simplify this. I guess I'll just erase this board with my stylus, which is not trivial. Actually, I guess I could have paused it while I did this. I just realized that, but it's too late. Okay, so for any protein-ligand interaction, we could write an expression for the dissociation of the protein-ligand complex. So P stands for protein and L stands for ligand. We know then that the KD is the concentration of products over reactants. And then theta is equal to the concentration of whatever the ligand is for that protein divided by the concentration of ligand plus the KD of that protein for the ligand. So this is for any protein ligand interaction that follows that hyperbolic shape. This is concentration of ligand and this is theta. You can use this expression to relate the fractional saturation and the KD value.